Right, it's top of the hour. So welcome to today's webinar. And the topic was an interesting one because I've been asked this many times about how mission time impacts the SIL verification. And of course, it's not just mission time, but it's a combination of mission time and the testing, the proof testing that we do that will impact the SIL verification. Now, of course, there are other variables that impact SIL verification as well, but these three are very important, as we shall see. So for those of you that are new to Exida's webinars, we normally like to do a short introduction about the company and what we do. Those of you that are used to our webinars, if you could just bear with me for a few minutes, it won't take too long. So just a little bit about Exida. Exida has been around for 25 years in January. Exida is short for Excellence in Dependable Automation, and we now have three main divisions that deal with certification and assessment. This is where we do product certification for functional safety and cybersecurity, as well as personnel certification. Then there are the lifecycle services that we handle the life cycle for alarm management, cybersecurity, and functional safety. And those three together, of course, are very important when it comes to overall process safety, because we have to look at the consequence of compromise if we have a cybersecurity incident. We have to look at the consequence of inaction if the alarms are not properly configured and the operators can't see the wood for the trees. And of course, there's the consequence of failing on demand of the safety instrumented system because we haven't either designed it properly or maintained it properly. So the full life cycle services provided, along with all the training, the corresponding training and procedure templates for that. And then finally, the enterprise tool. Some of you may be familiar with the Excellencia tool. So these tools are sold separately or together as a suite, and of course they're used by the engineering team. We are global. We've basically got offices in most regions of the world, and the last one we added was in Ireland, just around the or just before COVID hit. And the nice thing about the three disciplines, the functional safety, the alarm management, and cybersecurity, it's what we like to call industry agnostic. So we can apply it to any industry. And of course, that involves the automotive industry, as well as robotics. And now AI, of course, is being used more extensively. It also applies to machinery. So we're doing a lot of machine safety, and our Irish office is ANAB accredited for the European directive. We also work in mining, we work in steel, we work in energy, water, chemical, and of course oil and gas. We've moved away from being just originally owned by the two founders to being more employee owned now. And we've also got the largest market share when it comes to device certification. We do have well over 100 global experts now, as well as done well over 1,000 certification assessment projects. And of course, Excellencia is used extensively for doing SIL verification and SIF modeling. Reference materials, we publish a lot of things, not just for sale, but we also publish a lot of information free of charge. So these webinars, for example, and they're recorded, of course. So they're available via YouTube, and you can get to those through the website. And I always encourage people to make use of that. It's a very valuable resource to use. And of course, we cover functional safety, we cover certification, we cover cybersecurity and alarm management. You can also purchase books through the website, and these books are readily available. And the last one was the one I did on functional safety for managers, because managers need to know what's involved. So a little bit about me, for those that you don't know me, I've been in industry now for 47 plus years, and I also, amongst other things, am the primary instructor for the functional safety. I also teach the cybersecurity, but I head up the engineering team and have global responsibility for some of the subsidiaries. So before we start, let's just take a safety moment. And oftentimes what happens, especially when it comes to why accidents occur, is because people sometimes take shortcuts in order to get things done. And the trouble is, when you take shortcuts, you can expose yourself to much higher risk. So the temptation should be avoided to take shortcuts, because accidents at the end of the day can be fatal. And if there's no fatalities, they can still be very expensive. So we want to obviously minimize the possibility of doing that. And even though shortcuts may seem to save time initially and cost, they could actually end up costing you a lot more in the longer term. And is it really necessary? Would you like to be this guy with the board on his back and trusting your fellow colleague to use that saw carefully? So it's something that we have to avoid. And oftentimes I come across this a lot, where people are trying to save money and thinking that they can cut corners, they can delay doing the maintenance, delay doing the proof testing, and all of that, because they think, is it really necessary to do that? And the trouble is, it is necessary to do that if you want to maintain your risk. So, coming on to the main point of this webinar today, another question I often get asked is what is mission time? What do we mean by mission time? And mission time is sort of a throwback from the Second World War, where when the bombers needed to go off on their missions, the engines had to be reliable enough to carry them there and bring them back. So this sort of concept of mission time has stuck. And from the 1511 point of view now, we require that the time we expect a set of SIF equipment to work before a major overhaul or replacement needs to be stated. And this is what we refer to as the mission time. And the other thing is, the end user should be specifying what the mission time is, because it will be a factor involving their normal practices. So what are the end user practices when it comes to the mission time? So for example, it could be that they have a 5-year turnaround. And so you might set the mission time at 5 years, or you could set the mission time against your valves, for example. So if your major cost is the refurbishment or replacement of valves, then you might set it for that, which could be 10 years, for example. Others might say, well, we'll have to change out the logic solver in 15 years, so that's going to be a major change, so we should set our mission time at 15. Others arbitrarily set it at 30 years. But the point is, it's the end user that needs to determine that, and not the engineering company, because the end user has to obviously track and maintain that. But we mustn't also lose sight of the fact that even if we set the mission time at 10 or 15 years, we have to look at the useful life of the devices in the SIFs. And it may be that if we've got actuators, for example, those may need to be either replaced or refurbished every 5 years. So if we've set our mission time for the SIF at 10 years, we've still got to change the actuators at 5 years. And there's another webinar that I did on why we have to follow useful life. So I'm not going to go into it here. But if you want to understand more, I would recommend looking that one up in the recorded webinars. So why is mission time important? It's important because SIL verification is very dependent upon mission time when we're not assuming perfect proof testing. And I'll talk about that in a minute. It is a key part of the calculation. And as we shall see, there's a direct correlation between proof test coverage. And what we mean by proof test coverage is the ability of a proof test to help us find dangerous failures. The interval, how often are we going to proof test, in conjunction with the overall mission time. So like I said, SIL verification does depend on a number of variables. These three are also part of that, and they're an important part of that. So just to refresh our memories on what do we mean by proof testing. The purpose of a proof test is to help us find any dangerous undetected failures that the automatic diagnostics have not been able to find. It's not to prove that the SIF works. And this is why it's very important that if you don't have a tool like Excellencia, which has this information in it, you need to look at the recommended proof test from the manufacturer. Now, of course, with a safety instrumented function, it's made up of multiple pieces of equipment. And those pieces of equipment will all have different requirements in terms of proof testing. So you need the safety manual, because the safety manual will have a recommended proof test to achieve a certain coverage for finding dangerous failures. So it's important that you have access to that safety manual. And very often when I talk to end users and even teaching the classes, when I ask the question, do you have your safety manuals? And some clients say, yes, we have the safety manuals, but others say, no, we don't. And the thing is, when it comes to certification, IEC 61508 specifies that there should be the proper end user documentation, which is a safety manual. The thing is, with that, is it doesn't necessarily mean that they will give it free of charge. And indeed, some suppliers will charge for certain portions of the safety manual. The safety manual could also be part of some other documentation as well. But the point is that you have to make sure your purchasing people, when they order the equipment, they also specify a safety manual has to be supplied. Because as I've said, we would need to study the safety manuals and come up with an overall proof test for the SIF based on the equipment that we're using. So this effectiveness, the proof test coverage, is referred to. That is how effective is our proof test at helping us to find dangerous failures. And as I've said, we need that safety manual to be able to follow that guidance. This is very important because, again, coming back to my point about how is the PFP impacted by these three variables. Mission time in conjunction with the proof test interval, in conjunction with the proof test coverage. These three. And it will be impacted by a combination of all of these three. Now, if we consider the simplified equation for probability of failure, and this is a simple formula. During useful life, and again, as I've said, there's another webinar that covers the reason why we have to track useful life. But during useful life, we can claim constant failure, in which case we can say that the probability of failure for the SIF is going to be the failure rate times the time interval. So this is at its simplest form. And this is based on the premise of perfect proof testing. What do we mean by perfect proof testing? If we assume that the coverage for dangerous failures is perfect, then what we're saying is that we can find and fix all the dangerous failures during testing. This is a fallacy, of course. It's not possible to claim that we can find and fix all dangerous failures. And this is very important because if we consider perfect proof testing means that mission time has absolutely no bearing on it. Because again, if our coverage for dangerous failures, which is obviously going to be a function of the dangerous failure rate, known as lambda d, then we simply would be saying that our PFD in this case, probability of failing dangerous, would be a function of lambda d times Ti. The mission time has no bearing, because what we're implying is if we can find and fix all the dangerous failures when we test, what does that do to our PFD? Well, it basically means the PFD is 0. We found and fixed all the problems, so we don't have any probability of failing on demand after each test. So effectively, we're resetting to 0 every time we do a test. So this is a fallacy, and it's completely unrealistic, because there's no such thing as a perfect proof test. And the PFD average, of course, which is half the PFD, would be the same, lambda d times Ti over 2 in this case, if we assume perfect proof testing. However, if we come back to the real world, if our proof test coverage is not perfect, then we cannot simply say that our PFD is lambda d times Ti, or our PFD average is lambda d times Ti over 2. Because now we can't find and fix all the dangerous failures. So instead of returning to 0, the PFD will not return to 0. It'll be at some level above 0. And this is often a conversation I've had in the past with different clients. If you think of it this way, if we consider a safety function has a butterfly valve, a pneumatic single action actuator, and it's implementing a close to trip function, even if we do a full stroke proof test of the actuator valve assembly, and we confirm that there has been rotation, are there still any potentially dangerous failures? And of course, the answer is yes, there are, because we don't know what's going on inside the valve. There could be a damaged shaft, there could be damaged seals, there could be damaged butterflies. So we cannot say that a full stroke is 100%, and I have heard people say full stroke is 100%. There's absolutely no way you can say it's 100%. Because as we shall see, if you assume perfect proof testing, you're just fooling yourself. So we know then, if we have perfect proof testing, that the assumption is the PFD will be 0 after every single test, and mission time has absolutely no bearing. But now if we accept the premise that there is no such thing as perfect proof testing, we have to consider the mission time. Because if our CPT is not 100%, then of course the PFD is not going to be 0 after the proof test has been completed. And therefore our simple formula has to account for imperfect proof testing. And mission time now has an impact, because we can't say PFD is simply going to be lambda d times Ti, or PFD average is lambda d times Ti over 2. Because instead of it going back to 0, we're going to have a portion here that we can't find every time we do a proof test. And using our complement rule, if we said that the coverage factor was 80%, that means that we can't find 20% every time we test. So this will be dangerous failures that the proof test can't find. So now we have to account for that. And this is going to be cumulative over the mission time. So it's no longer simply going to be lambda d times Ti over 2. we have to take into consideration the coverage. So the dangerous failures we can find governed by CPT times the dangerous failure rate times the proof test interval. But now we have to add in the dangerous failures we can't find, which is governed by 1 minus CPT, over the mission time. So now we have to include the mission time. So you can see mission time now will have a direct bearing when we don't have perfect proof testing. So to illustrate that, let's consider a simple example. Let's say that lambda d is 2 times 10 to the minus 7 failures per hour, or 200 fits. Our proof test interval is 10,000 hours. In this case, we're saying our coverage is 90%, and our mission time is defined as 200,000 hours. So, using our simple approximation equation, we need to compare the result with the perfect proof testing. So, of course, if we assume perfect proof testing, we've got the same failure rate. We have a test interval of 10,000 hours. Our CPT now is 100%, and our mission time is still 200,000 hours. So let's look at the first. Using our simplified formula for imperfect proof testing, where we're taking into consideration the failures we can't find, and we plug in our numbers. So we have our coverage factor, which is 90% or 0.9, times the failure rate, which is 2 times 10 to the minus 7, times the test interval, which is 10,000, or 10 to the 4. So the 2's will cancel here, and 10 to the minus 7 times 10 to the 4 is 10 to the minus 3, so it's going to be 0.9 times 10 to the minus 3 on this side. Over here, we have 1 minus 0.9, which of course is 0.1. The 2's cancel out again, so now we've got 0.1 times 2, which is 0.2. 10 to the minus 7 times 10 to the 5 is 10 to the minus 2. So now we have 0.002. And if we add those two together, we get 0.0029. And if we invert that to get our RRF, so RRF is approximately 1 over PFD average, we get 345, which would say this was a lowish SIL2. However, if we assume perfect proof testing now, using the same formula, if we plug in our numbers, now we have 1, because CPT is 1, times 2 times 10 to the minus 7 times 10 to the minus 4. So of course these two cancel, and we've got 10 to the minus 7 times 10 to the 4, which is 10 to the minus 3. So we've got 1 times 10 to the minus 3, and of course this is 1 minus 1, which is 0, which means this completely disappears, because anything times 0 is 0. So mission time doesn't come into it, and therefore we're left with 0.001. And if you invert 001, of course, you get an RRF of 1,000, which says this is SIL3. So you can see, and this is the difference between 90% and 100%, which is only 10%. We're almost overstating our risk reduction factor by 3 times. So this is why I say, if you assume perfect proof testing, you're just fooling yourself, because you're overstating the risk reduction you can achieve by not using realistic numbers. And you can see here, almost 3 times. Why would we want to do that? We're just completely overstating the amount of risk reduction we have. So this is very important. So we need to understand that. Let's take another example. Let's just assume a very simple high pressure protection SIF, which is simply going to be a pressure switch, solenoid valve with a manual reset, an actuator and a ball valve. And let's say the SRS requirements were for this to achieve a SIL2 with a risk reduction factor of greater than 110. And in this case, we're setting the proof test interval at 3 years, which is fixed based on the plant turnaround. The mission time is defined as 30 years. We'll use a 90% coverage factor. There's a manual reset and it's hardwired, so there's no logic solved. So this is fairly simple and straightforward. Now, if we look at this in Excellencia, the mission time becomes an important part of this with imperfect proof testing, as I've said. And here you can see there's our mission time of 30 years. So the SIL target is SIL2 with an RRF of 110. Now, based on this design, we can only achieve a risk reduction factor of 35.9. So we're well off our target. And you can see over here that the final element is the main contributor to the PFD average because we're using a single set. So this is where we would obviously need to focus our attention. So in our example, we have a fixed 3-year proof test interval that's set by operation, so we can't move that. And here again, I always tell designers, don't design in isolation. You need to go and talk to the O&M guys and find out what are the end user practices. Because, and we had it where a client came to us because in order for the engineering company to meet SIL target, they had set the proof test interval at 3 months. And of course, the end user said, there's absolutely no way we can do 3 months. So we need to make sure we understand the operating conditions and of course the practices. Even with a 90% coverage, we can't meet target. So what are our options? We could look to increase our proof test coverage, but at 90%, the chances of improving it significantly enough not going to happen. We could include partial stroking. Now here again, when we are considering low demand operation, and especially with the final elements, we are concerned with failures such as stiction, cold welding, binding. All of these are dangerous, and especially when the valve isn't moved for long periods of time. So if we can move the valve, even a little bit, we know it's not stuck. And that can obviously alleviate quite a few of the dangerous failures. Now, will it properly close? Will it properly seat? That's a different matter. And if the device is capable of being partially stroked, and of course the process is such that we can move the valve, and usually the manufacturers will say you could move it, between 10 and 15%. It really depends upon the device and of course the application. But if you can move it, then you can obviously eliminate some of the dangerous failures. Not all of them, but quite a few. So that's one thing we could look at doing. And we could also look at reducing the mission time, of course, or we could add redundancy. So the simplest thing to begin with would be to add in partial valve stroking. So we can see here, if we set it up to do partial valve stroking automatically, and every 5 days, it gets us to 71.8. So we've more or less doubled what we had before, but we're still way off 110. So obviously partial stroking on its own is not going to help. The next step would be to see if we could reduce the mission time, because we don't necessarily want to jump straight away to adding redundancy, if we can help it. And according to the 1511 table, with a hardware fault tolerance of 0, we should still be able to achieve SIL2. So if we look here, if we reduce our mission time down to 10 years, and that coincidentally happens to be the useful life of this particular valve, then you can see we've actually achieved our target. We've got to 113, which is above our 110. So obviously with partial valve stroking and the mission time set at 10 years, we could achieve that. We could achieve our target. If we can't reduce the mission time, if we leave the mission time at 30 years, then we have no choice but to go to a redundant architecture because we're stuck with our 3 years. So if we can't move the 3 years, and so oftentimes that happens, we've had clients that say, well, yeah, one particular case, it's every 4 years, and we're not going to change that. So of course, that is going to be one of your 3 that's going to impact. And that means we've got the other 2. Now, if proof test coverage is relatively high and we're not getting there, then if we can move the mission time, that's fine. If we can't move the mission time, then we're pushed to go to a 1 out of 2 because it's the final element that was contributing to the PFD average. And you can see we don't need the partial valve stroking in this case, and we can get to 136. So we can still meet our target. So like I said, those 3 together, looking at the proof test interval, the proof test coverage, and the mission time is very important. Those are not the only 3 things that influence the PFD average. There are 9 variables in all, but these 3 are also very, very important. Okay, so let's just summarize this. Understanding the relationship between those 3 is very important. So when it comes to setting proof test intervals, from the designer's point of view who's designing the SIF, they need to understand what are the end user practices. Do they have determined shutdowns that they use to do this, turnarounds? In which case that has to be one of the factors. Making sure that we don't assume perfect proof testing, because you saw what happens if we do that, and then looking at what we can achieve as a coverage and balance that with the mission time. So as I've said, the mission time selection is the end user, and that will be based upon how they view things. Now, oftentimes they don't understand this relationship, and that's where guidance is obviously important, understanding it, hopefully educating so people understand that these things do have an impact. And of course, the higher the SIL that you need for your SIF, the more critical this relationship is to meet target. So if you do set your mission time at a high level and your fixed proof test interval is relatively high, so for example, if we said proof test interval 4 years, mission time 30 years, and we're limited with a coverage up to 90%, and we have some high SIL2s, they may not make it in a single architecture. So we may have to be looking at, in the first instance, if we can partial valve stroke, that may help us depending upon the amount of risk reduction. So if it's a SIL2 with a risk reduction up at around 600 or 700, then you're probably going to struggle without going to a redundant architecture. Remember, perfect proof testing is a fallacy and it's completely unrealistic. And I know people will argue that, but reality is if you assume perfect proof testing, you're simply fooling yourself. And you're overstating your risk reduction, and you could be putting yourself into a much higher risk as a result, because you believe you've got better protection than you actually have. So it's important, again, to work with operations during the SIF design, as I've said, to set realistic proof test intervals so that you're not setting the O&M team up for failure. And again, part of that would be to recommend running through all the proof tests as part of the PSSR before you start up, because it gives you a 2-for-1 in that instance. Firstly, it'll give operations confidence that the proof tests are practical and they can actually run them. And number two, you might actually find some problems from the commissioning. And this would be effectively proof test at time zero, because if you don't do the proof tests and you start up, your first proof test might not be for a couple of years. So if you do have any potentially dangerous failures in the SIF, you won't necessarily find them until you do your first proof test, or if there's a demand on that SIF and it fails. So it's important to make sure we set realistic proof test intervals. It's important that the proof test procedures are usable, because you can design the best proof test in the world, and if it takes 10 hours to implement, guess what? It's not going to get done, at least not the way it was intended. And of course, if the coverage was significantly high, then you're not going to achieve the level of coverage. In all of this, we still have to track the useful life, because remember, the useful life is very important because of the premise of constant failure during useful life. And as I've said, if you want to know more about that, there's a video, and also there's a webinar that was done on this. The proof test procedures need to follow manufacturer's recommendations to achieve coverage. This is very important. Unless you're very, very familiar with the equipment, you've used it for some time and you've developed proof tests that you know are just as good, that's fine. So these are the things that need to be remembered and understood. And I see that there are some questions brewing, so we'll get to that. Let me see what we have here. Okay. So this one says, under reliability considerations of the components like shaft or seat of the butterfly valve, fail to trip actuator spring, will make sure to close the valve, and this proof testing is 100%. No, it's not 100%. You can't claim 100%. Same issue as I said. You don't know what's going on inside. So when I say imperfect, I'm meaning it's not 100%. It'll be some percentage, but not 100%. Then what will the effect in voting system 1 out 2, 2 out 2, 2 out 3? Well, as I explained to you, if you have redundancy, depending upon the type of configuration you've got to start with, you, as I showed you in this example, you can meet the target. So that's an option. And as I said, if we balance that out, if we can't move the mission time, if we can't move the proof test interval, and we can't improve the proof test coverage, then that's probably the only option we've got, if partial valve stroking isn't going to help. Many safety manuals just reference the 8 to 12 years useful life from the 1508. It's hard to convince operations to adopt that lifespan in the real world. What is the realistic approach to extend the device mission time beyond? Well, here again, that's where you have to look at the safety manual. Now, the safety manuals, I can tell you from Exida's point of view, we will check the safety manuals to make sure that they comply with 1508 requirements. And the purpose of the proof test is to help us with extending the life of the device. But it's still, there's going to be a maximum limit that we have to be able to track. Remember, the concept and why useful life is very important is everything we do in functional safety and reliability calculations, the PFD calculations, everything we do is predicated on constant failure rate during useful life. Once you get outside of useful life, you can no longer claim constant failure. It's completely unpredictable, and therefore you don't have a PFD average you can rely on. You don't have a SIF you can rely on, because you don't have a SIL you can rely on. So you have to make sure you track useful life. That's why I say this has to be completely understood. Most end users are more concerned about spurious trips and dangerous failures. After a few spurious trips and production losses, they tend to bypass safety interlocks. Yeah, well, I understand that, but here again, if the part of the reason why spurious trips occur is either because of poor maintenance or because procedures are not being followed properly and people are causing spurious trips. This is why the 1511 standard now requires us to do an FSA 4. Because remember, it's a performance risk-based standard. And a performance-based standard is different from a prescriptive standard. Because a performance-based standard will say this is what you have to do, but how you do it is up to you as long as you can measure your performance. So of course, when the SIF is designed, the SRS, the safety requirement specification, should have a target specified for the mean time to fail safe, in other words, the spurious trip. And when the SIL verification is done, it should also indicate whether or not the SIF meets the mean time to fail safe. So that mean time to fail safe will also be a function of the testing, the test interval, the coverage, and of course the architecture. Now, with 1 out of 2, we get a much more improved PFD average, but of course we sacrifice spurious trip. But as long as the spurious trip is within the target set in the SRS, and as long as we're following the proper maintenance procedures, then we should reduce the prospect of spurious trips. But again, this comes down to site practices. So if the end users are experiencing a high number of spurious trips, there is either some underlying systematic that needs to be looked at, or they're not doing the proper maintenance. So I would not accept that argument. And if they bypass safety interlocks, then again, they're just increasing their risk. And that's part of the problem, of course. It always comes down to that. So spurious trips, I agree. We want to try and avoid that. But if we design the SIFs properly, if we maintain it, because remember, the old adage of 20-20-20, 20 weeks in design, 20 months in implementation, 20 years in operation. So the majority of the lifetime of the SIS and its SIFs is going to be spent in the O&M side. And if the operations and maintenance are not following procedures properly and they're not doing the proper testing along with following the mechanical integrity and tracking the useful life, then yes, they're going to experience much higher problems, either incidents or spurious trips. What would you recommend to avoid spurious trips? Well, I think I've just covered that. Can I receive a continuing education credit for this course? I don't know what you mean by this course. I mean, webinars, yes, you can get ongoing credits, so that's true. Any training course you do, of course, you'll get credit for. How can be defined better proof test coverage? What percentage to? Well, as I said, you have to have the safety manuals, and then it's looking at the safety manuals and creating a proof test for the SIF based on the safety manuals. If you have Excellencia, and depending on which version of Excellencia you have, if you have the ultimate version of Excellencia, it will automatically generate proof tests based on manufacturer's recommendations and also based on the equipment you've defined for the SIF. Otherwise, you have to go to the manufacturer's recommendations to come up. So, should the test scenario of the proof test be changed from time to time? Well, again, you see, this comes back to what I'm saying about performance. The FSA 4, the purpose of the FSA 4, which is now a mandatory requirement under 1511, is to be able to prove that we're meeting our requirements. Now, if we're finding that our performance is better than the original target, then yes, you can, by looking at and studying the data, you could then say, well, we could extend our proof test interval and not do it so frequently, and then recalculate based on that. That's the whole purpose. The purpose of doing FSA4s is, number one, we need to have a good quality data gathering system for the field data, which means that if we have any failures, we do the proper analysis to see, okay, was it a safe failure? Was it a dangerous failure? And remember, dangerous failures are either found as a result of proof testing or because there's a failure on demand. And was it random or systematic? So there are other webinars I've talked about the difference between random and systematic and why it's so important to make sure we capture all the random failures. So I'm not going to go into too much detail here, other than to say we need to capture the correct number of random failures. Otherwise, what happens is you end up with very low random failures because you're not classifying them properly. And that ultimately leads to dangerous assumptions on failure rates. If dangerous undetected failures are random throughout the mission time, how are the how is the useful life determined? Well, the useful life is determined by the manufacturer. And when we do FMEDA analysis, we can predict what the future, the mission time is going to be. And again, in Excellencia, you can look at the data sheets for the devices, and it'll define in the data sheet what the useful life is. If not, it should be in the safety manual. If it's not in the safety manual, you have to go back to the manufacturer and make sure you get that mission time. Sorry, that useful life. Can the useful mission time be higher than the useful lifetime? Well, yes, of course. That's why I said the end user chooses the mission time. So even if they choose 30 years, if the valves need to be refurbished or replaced after 10 years, they would have to do that at least twice before the end of the mission time. So you still have to track the useful life and make sure that they are either replaced or refurbished as good as new. If the valve is proven in use by end user, let's say similar equipment used in one plant and now want to use another plant, does the mission time or calculations matter? Yes, of course it does, because here again, you have to make sure that with prior use justification that the devices are still within their useful life, and you can determine that by doing a FMEDA. And also, if you're trying to use it in another application, as long as the application is the same or similar in terms of the operating environments and the environmental conditions, then you can claim the prior use justification, but it still needs to be within its mission, within its useful life. If CPT is not 100%, then what to consider? As I've said, you need to have the safety manuals to see what's recommended and then come up with a proof test for the SIF. And you can do it based on a weighted average, which is how Excellencia does it. So it'll look at each piece of equipment, look at the proof test coverage, and again, you can either choose to use the proof test coverage from that's recommended, so it'll calculate a weighted average and apply that, or if you choose to override that, you can do that. But again, if you go to 100%, you're just fooling yourself. The major challenge in a project are the on-off valves and the useful lifetime for some 3 years or 6 years, at the end of which a major overhaul shall be done. This becomes complicated. When clients request RAM 25-year operation and overhauls every 3 years, when a project has 254 on-off valves under SIF SIL 2. Well, again, as I said, you have to be tracking that, and you have to follow the useful life requirements. So that's why I say the end users need to determine test intervals and, of course, what they're going to choose as a mission time. But it needs to be done with the knowledge of the impact for operations. So the useful life has to be tracked. We have to make sure that we have a program to do the refurbishment or replacement. So we end asking the vendors to extending the useful life mission time. Well, yeah, you can. That's why I say you need the safety manuals. You need to know what's being recommended in terms of a proof test and coverage, and you need to know what the useful life is. Can you please share the equations for PF average calculation, considering all these factors? Well, that's, again, that's what we get paid for. But you can find these calculations, you can find the simplified equations in 1508. There's another question here. Can I ask why you think it is the standards don't specify, mention mission time? Well, because mission time is something that's set by the end user and it's not mandatory. Remember, 1511 is a performance risk-based standard, as is 1508. So they're not prescriptive. Prescriptive is, it tells you what to do, but it tells you how you have to do it, and there's no leeway. So with a performance-based standard, it says you need to determine what the mission time is, you need to determine what the mean time to fail safe is. It doesn't tell you what that needs to be. And so it's up to the end users to define that. So again, these things are not mandated in terms of specifying values that you have to use. It's saying that you have to specify it, but whichever one you want to use is up to you. So again, if we say that our proof test intervals are going to be set at 2 years, then as part of our ongoing FSA4 activities, we should be checking to make sure, are we doing it every 4 years? Because again, another thing to bear in mind, and this is subject of another webinar I did, is if you get more than 10% outside of your proof test interval, then you're going to start impacting the risk reduction factor for the SIF. So, and usually if you miss it the first time by 10%, you're likely to miss it the second time by 10%. And of course, now this is becoming a compounding issue, which means that your SIF performance will drop off a cliff very quickly. Yeah, again, so useful lifetime from the on-off valves vendor, how serious is it? Well, as I've said to you, remember, everything we do in functional safety, all our calculations are based on the simple premise of constant failure during useful life. As I said, there's another webinar on this. You're more than welcome to check that out. Plus, I think I did a video on it as well. But the thing is, if you get outside of useful life, you can no longer claim constant failure rate because it's very unpredictable. So whether it's an on-off valve or whatever type of device it is, once it gets outside of useful life, we cannot rely on constant failure rate. So we don't have a SIF that we can rely on. We don't have a PFD calculation or a PFH calculation we can rely on. So it is a very serious thing to make sure that we track useful life. And many times when I talk to clients, they're not doing this. Do SIL study is done for BMS systems? Yes, it is done. We do SIL studies for BMS systems. Is it the same as ESD systems? It depends. If they want to do it to the 1511 standard, then yes. And I'm being asked whether I have an example of an FSA stage 1 and stage 2 checklist. Yes, we do. Can you please explain FSA level 4? If you haven't studied the standard, then you won't really understand this, but functional safety assessment level 4 is to look at performance. So the standard defines it as being some period of time after operation. So you've experienced some operation, then you should be able to go and look at. And remember, an FSA 4, and any FSA for that matter, there are two fundamental objectives of performing a functional safety assessment. The first is to provide, and here's the key word, an independent cross-check on safety. So it needs to be performed by someone or a third party not involved in the design or not involved specifically in this particular part of the life cycle. And secondly, it's to help us identify potential systematic issues. So there's another webinar that I did on systematic if you want to watch that. But you need to look at the standard. You need to understand the standard. If you're functioning or operating to 1511, you need to understand why these things are important. Please confirm, looking at slide 15, summarizing the math, both the PGI and the MT are directly proportional to the inverse of the RRF. Well, the inverse of the RRF is the PFD average. So there is a correlation between PFD average and risk reduction factor. And if you look at the 1511 or 1508 tables for low demand, you'll see it has that relationship. The contributions to PFD average are additive. Well, as I said to you, you can see in the simple formula that I used, and it is too simple to use for any real calculations because there are so many other variables that they don't consider. But you can see that every time we do a proof test, it's going to accumulate over the mission time, those dangerous failures that we can't find, and that will have an impact on the PFD average, as you saw in the comparison. In theory, this while going down Route 1H, how does all this work on proven in use? Or I'm sorry, I don't understand that question. You need to email me. And then we are talking about electrical, programmable electronic one will be the impact of the M17995. Well, it just, here again, if you are looking to follow 1511, and 1511 is the recognized process industry sector standard, which now not just covers chemical and oil and gas, it now covers pharmaceutical and food and beverage. So if you're looking to follow RAGAGAP, recognized and generally accepted good engineering practice, and 1511, then it's really, you need to follow the requirements of 1511. Okay, then it says, in theory, this works while going down Route 1H. How does all this work with prior use? Well, as I've said, you can't, even if you're going prior use, you still, so there's two things. If the manufacturer is claiming proven in use or prior use from the 1511 perspective, which is more the application, they still have to provide a safety manual. They still have to have a useful life defined. So again, if you don't have that, because the purpose of prior use is from the systematic point of view, to prove that we have any dangerous failures we've had due to a systematic cause are low enough that they're not going to be a problem for the SIL we're trying to claim. And that also means that we have to meet the random failure rate. And the only way you can meet the random failure rate is either by doing some form of FMETA or some quantitative assessment of the random failures for the device. So this is important when it comes to claiming IPLs, independent protection layers. And we go through this in a lot of detail when we do the FSC 100 class. So if you're interested to know more, I would recommend you sign up for that class. Useful life value used in PFD calculation. Right, well, okay, I'm not sure. Yeah, you just have to, I'm not sure what this question is asking me. How to define, estimate the test coverage? Well, as I said many times, I usually refer to this in class as RTFM. Read the flaming manual. You need to look at the safety manual unless you've got Excellencia. Can we take a DCS loop as SIL 1 in Excellencia, I think you're trying to say. Well, that depends. It's there's a lot behind that. I think, again, if you want to know more about that, you'll have to email me separately. All right, well, that's a fair number of good questions. We're just about out of time, so I thank you all. If you have any other questions, feel free to contact me at this email address. I'm happy to answer them. So thanks for listening, and until next time, take care.